So my name's John Shakshober. Shak is my nickname. My first name is actually Douglas, but I keep it kind of hidden to be incognito. And everyone says that I really don't look like Shak, so usually very disappointed to meet me. We have with us Larry Woodman.
Yeah, I'm Larry Woodman. I'm one of the engineers in the Red Hat Enterprise Linux kernel group. I've been there for about, going on 13 years now, so.
And then also we've added a member of my team that does performance engineering. He's been working a lot with our field and top tools, and essentially is our network expert. A lot of Red Hat being used in cloud environments need to depend on network performance critically beyond just the normal VM and disk. And so with that, I'll introduce Jeremy.
Hi guys, Jeremy Eater. Yeah, I work for Shak. I do some networking stuff and some container stuff more recently. And we'll try and relate some of that experience to on Red Hat's newest products during the next 2 hours, separated by lunch.
Very good. So we'll get started. Here's our slide outline, if you will. And we are going to move fairly quick on the slides. Do not worry. We're going to give you the slide decks. We're going to give you pointers to other documents that are performance tuning guides. There's actually a full week class in tuning from Red Hat called Performance RH440, I believe, is the number. And but part one here is this first hour. We're going to kind of share a little background. I'm going to go through some of the evolution of RHEL. I've been able to be at all 10 summits now, so I've been here about 10 years. Larry's actually my elder. He's been here, what?
No, well, same number of summits, but.
Same summits, 12 years, I think, working at Red Hat, and Jeremy's just turning the 5-year mark, I believe. Okay, so we're going to cover some of the newer non-uniform memory optimizations, Cgroups and containers, so containers and RHEL Atomic were introduced at this summit here, so we're going to share some of the vision and the roadmap of those and how we're going to evaluate performance. We're going to go through the scalability, the scheduler in Linux, both Red Hat 6 and Red Hat 7, and some of the use of, in x86, it's called Hugepages. So just a show of hands, how many people are running Red Hat 3 today? Okay, I'd like you guys to exit. No, I'm just kidding. That is cool. Again, we're still with you on that. Red Hat 4, show of hands. Okay, little more, but still not a. How about Red Hat 5? Oh, wow. So we have a good population of 5. So we've been given these talks. The talks are available. A lot of the tuning still applies in 4 and 5 and somewhat in 3. But Red Hat 6 and 7 are kind of what we're going to share as an evolution. And in fact, without further ado, some of the evolution is, in fact, Linux is a very tunable operating system. It's fantastic. Many of us have Unix backgrounds. Essentially, the hardware can be tuned and optimized in multiple dimensions. So some of the things in Red Hat 5 that allowed us to really put the word enterprise into Red Hat Linux really is available in Red Hat 3 and 4 as well, the use of Hugepages. You would have to manually tune that. In Red Hat 5, we provided a service called Ktune that allowed you to reset some of the sysctl parameters to more server-like settings, and it was a binary function. So we're going to show you how that's evolved in RHEL 6 with tunedies, and you're allowed to choose different profiles to optimize your performance for either latency or throughput. And so what I'm going to do is we can take questions on the tablets, but we'll attempt to answer some of them at the end of the session, but you can send them in if you want, or we can do it both at the end of the session and at the booth. There's a lot of performance engineers. Finally, CPU affinity. It goes through cores and mapping processes and threads to cores has been available day 1. Again, a manual process in RHEL 5. Schedulers do that automatically, but more and more the schedulers are becoming more aware of both the caches and architecture of x86, and in RHEL 7, in fact, there's the ability of the scheduler to know about the NUMA environments, non-uniform memory. And then the same things when you get to the devices. So whether it's a network device, an I/O device, etc., your interrupt requests, your IRQs, have a service called Autonuma-Balance. That can be, that's been optimized over the years. And then finally, it's something you can manually disable and use some of the tools like Tuna, or Tuna's the recommended one that came out of our real-time group to manipulate IRQs. If you're familiar with the proc file system, you know where these structures are. You literally just dig through the structures, and you can optimize them through that file system as well. So as a background, and as we've watched Red Hat go from RHEL 3 to RHEL 6 and soon to be 7 later this summer, industry standard workloads have been used, and in fact are a good way to see performance of different systems. Red Hat actually doesn't publish benchmarks. We help our hardware partners, our OEMs, and our chip providers essentially optimize things running RHEL software, whether it's bare metal, virtualized, etc. So there's a number of SPEC, stands for System Performance Evaluation Committee. TPC is transaction processing and database performance. We get into this vendor-specific applications like SAP, and the Stack Consortia focuses on FSI markets. We also do some competitive benchmarking with, most people don't like Red Hat to do competitive benchmarking against, so why would you believe a report from us? So there's a company called Principal Technologies, and sometimes Intel, sometimes Dell, sometimes Red Hat, sometimes HP. Other vendors, we basically ask them to run our stacks, and we help them tune, and then allow them to run, whether it's Windows or other virtualization or cloud products. So they have a wealth of competitive data out there. But we're not sales, we're engineers. So this does show you, in 2014, when Intel launched the Ivy Bridge EX platforms, 10 years ago, a little history, we basically had about 5–10% of the benchmarks being done on Linux, and a lot of Unixes, and of course Microsoft had a kind of a lion's share of the benchmark results on hardware platforms. And so we now enjoyed, this is just the number of benchmarks results that were launched when Intel did the Ivy Bridge EX versus some of the other OSs here on the left. And then some of the other workloads as we, literally the percentage of workloads that are using Red Hat Enterprise Linux or KVM virtualization or other Java workloads. So in fact, we are glad to see the vendors and OEMs optimize with Red Hat. We're really more important to us, rather than winning benchmarks, is actually making real customer applications perform. And that's really the goal of the industry standard loads is hey, let's do representative workloads that the industry is using, so that the benchmark should reflect some workloads. And so in fact, the left side we're open source, so all these benchmarks are available. We're going to share some results, some performance differences between releases. And the good news is, if you can't find them, give us an email or a call. We'll help you, at least find the benchmark workloads, share a little methodology on how to do benchmarking, and try to understand. Quite frankly, we believe, I'm an old hardware engineer, I believe software and the OS should literally do the application function as efficiently as possible and get out of the way. So Larry and I always have a nice quandary on that, because he's the guy that has to help me make the OS get out of the way. Right side is we do a lot of applications. So the good news, as you are investing in Red Hat technologies, we try to make sure the performance of the newer release is as fast or faster than the previous release. So a quick little dashboard. Those in the front, you still can't read the bottom line. Those in the back, you might see the squiggly line like a heartbeat. But in reality, the blue lines are essentially the RHEL 6.5 baselines of the network and memory workloads, disk I/O and databases, whether it's Oracle, DB2, Sybase, etc., whether it's NoSQL, Postgres, MongoDB, MariaDB, etc. Our team runs a whole suite of applications. You get into the SAS and the SAP at the end. And the little heartbeat, the red bars are RHEL 7 today. Some of the benchmarks are time-based, so lower is better. But the bottom line is that blue bar is the difference between the bars. And so our goal is to make sure we hit 100%, and then sometimes we're seeing 12, 10, 8% improvements in performance. And these are workloads that don't necessarily take advantage of any new features in the OS. So it's important to be able to maintain the current performance and give you more added value in the future. And so with that, we're going to switch gears over into the tuning, and I'm going to let Jeremy Eater jump right into what is TuneD for RHEL 7 and 6. Well, 7 in particular.
So for those on RHEL 5 or RHEL 6, mainly RHEL 6, you've probably seen TuneD. It was an optional service in the past. We've taken it one step further in RHEL 7 to install it by default, part of the core operating system, and to enable it by default in RHEL 7. From a high-level point of view, this is what TuneD is. It's a tuning profile delivery mechanism. What we do is we take our experiences and deliver them into the product via these tuning profiles. There are, I believe, 8 or 9 that we ship right now. There's essentially 4 or 5 or maybe even 6 that are performance related. There are some that are related to power savings or for desktops. For the performance team, we're generally interested in the performance profiles, of course. Now this is a little bit of a delay. So why do you care? This is why. This is why we went the extra step and enabled some of this stuff by default. When you get your hands on the release candidate, this is actually testing that's probably within a week or 2 of the release candidate kernel. So 1.11, and I forget what the RC is, but it's in that area. And you can see here that this is actually an IO zone benchmark, so a storage benchmark across 4 different file systems, using our tuning profile versus an untuned system, so baseline upstream Linux kernel. And when you apply the profile, you get 10 or 12, maybe even up to a 15% performance boost. It gets even better on the network side, 40 gig Mellanox, and on the right-hand side, you can see, you can get basically line rate after you use one of these tuning profiles. You could achieve all this stuff hand tuning on your own. It's not rocket science. There's no black magic to it. The profiles are flat text files. You can edit them on your own. And in fact, I'll show you how to build your own profile. So that was a network throughput. Also have a network latency profile, both new for RHEL 7. Most of the profiles adjust some of the power management. Network latency gets even more aggressive and can help reduce some jitter problems introduced by power management. So as I said, it's installed by default. Based on the variant that you install, you might get one of 2 different profiles. Balanced, which changes nothing from upstream. Same for the workstation. And the server variant of RHEL 7 will get the throughput performance profile. The code of TuneD itself was completely rewritten. It provides a compat package for the profiles that we shipped in RHEL 6, but there really should be no reason to use those. But we are going to ship TuneD profiles compat as a package. If you're familiar with the layout of files on disk in RHEL 6, there were 3 or 4 config files that you might have to edit. We've consolidated that all into one single file. So that's a little bit of a usability improvement. And we've also added the ability to call out to any other script that you want. So when you apply this profile, it may call out and do any other number of things, whatever you'd like. It also you can also daisy chain profiles off of each other. So instead of creating your own profile that replaces the default profile and is just kind of a copy, you could include one of our profiles and then make your changes that may even override some of the tunings that our profiles ship. We added, so RHEL 7 delivers a whole bunch of new features. Some of them are performance related, many of them are performance related, and the profiles have been updated to take advantage of those. Also bash completion if you're interested in that. So this is what the profiles look like right now. I mentioned the concept of inheritance. This shows you the 3 parent profiles and some children that inherit all of the tunings of the parents and then add some additional stuff on top. Where it's all designed to head is for you to take your own tunings that you are currently maybe scattered on the command line, maybe scattered in syscontrol, maybe some application initialization scripts, and you could potentially roll them all into a TuneD profile. Either it's a standalone or it's daisy chained off of one of our profiles. That's what it looks like when you run. So the interface, actually user interface, is tuned-adm. When you type tuned-adm space list, you'll see the list of profiles, and you can see the 7 or 8 or 9 of them that are there. Good job, Larry.
Okay. So I'm just going to talk about some of the features that we have in RHEL 7. One of the big pushes we have right now in RHEL 7, and even to some extent have backported into RHEL 6, is NUMA awareness in the kernel, so that the kernel can make intelligent decisions on what CPUs to run processes on, where to allocate the memory so that you optimize the performance. In RHEL 6, we have some sort of manual ways you can take advantage of the NUMA configuration, and a daemon or a service called numad that will dynamically move processes around so that they run on the same node that the memory is allocated on. In RHEL 7, a lot of this functionality has been moved into the kernel. It's a lot more efficient, a lot faster. The kernel has a lot more knowledge about the architecture than some user or some service does. And you can enable and disable it. It's on by default, and I'll talk about reasons you might want to disable it. So what is NUMA? A NUMA system is built up of almost a cluster, if you may, of computers. Each node in a NUMA system consists of CPUs, memory, some I/O connectivity, and internode connectivity to other nodes. It's the reason that NUMA systems were invented is they kept increasing the number of CPUs in an typical SMP system. After a while, the connection between the CPUs and memory just becomes saturated, so it would spend the majority of its time just waiting to get on the highway, so to speak, if you might. So what they did is they disconnected or built smaller systems with a local bus and a global bus that sort of connects them together. So almost all systems now are NUMA. If you have even some of the laptops and everything, if they have more than one CPU, more than one socket, they're NUMA. And there are actually some systems that have multiple NUMA nodes within a single socket. And then I'll talk a little bit later about interleaving memory and what that means. So this is what a typical NUMA system looks like. It's a 4-node system. Each node has RAM, CPUs, cache, and links to the outside world and to in between the nodes. This is a fully connected NUMA system in that from any node you can access the memory or the resources on another node with one and only one hop. On a lower end system, or one that is designed differently, the X in the middle might be removed. So if node 0 wants to access the memory on node 3, it might have to make multiple hops to do that. So as far as the kernel is concerned in hardware, there are per NUMA node resources. The memory, the kernel manages memory on a per NUMA node basis. It manages the CPUs, the I/O connectivity, the interrupt processing, and even the page reclamation. So if you watch a system run, there's a swap daemon called kswapd on each node running, independently of running on the other nodes. They're communicating with each other, but they're independent. And there are lots of other kernel threads or background activity that happen on a per node basis. So this is what a typical system looks like. This is just a small NUMA system with 2 nodes. Node 0 contains 3 zones, the DMA zone, the DMA32 zone. This is the first 16 megabytes and 4 gigabytes of physically contiguous memory that might be needed for certain devices that cannot communicate with more than either 24 or 32 physical address bits. And then the remaining memory on node 0 is what we call the normal zone. And then on node 1, all of the memory is just called the normal zone. So if you have a device or an application that needs memory in the first either 16 megabytes or 4 gigabytes, it must run on node 0, or it will have to make remote memory accesses with a significant performance degradation. So what I wanted to say is, this is putting the cart before the horse just a little bit, but when the system boots, it actually goes and looks in the BIOS and calculates the internode memory reference speed. And if that speed is not fast enough, what will happen is it'll set a tunable called zone reclaim mode. And if that tunable is set, when it exhausts all the memory on a node, rather than going and start allocating memory on another node, it'll start page reclamation on that local node, because the system determines that it's actually more expensive to distribute the memory among nodes than it is to just simply page and swap and get rid of stuff and run it all locally on that node. However, the reason I'm talking about this is there are several times in which the system, it does this based on the hardware, and you might have an application that does not live very well, or the performance is subpar because it's actually causing page reclamation to take place on one node rather than spilling onto another node. So what happens when, this is just a picture of what happens when the system starts reclaiming memory, and this happens on a per node basis. So all independently of each other, the system can be allocating, you can have processes allocating memory, and the system is aging pages and reclaiming memory and flushing it in and out of the page cache and so forth, independently of other nodes. And when this happens, like I said, it's possible that the system can swap and page when there's plenty of free memory available, and I'll talk a little bit later on how you resolve some of these issues, how you decide if that's a good thing or a bad thing, and if it is not, how you resolve the issues. So I don't know if you wanted to talk about this, Shaq. This is just we have a couple of multiple utilities that allow you to look at the hardware and see where stuff is. So here's the previous one was another one. Here's two other utilities, LSCPU, that allows you to look at what the configuration looks like in NUMA CTL ---- hardware. I use that one all the time. It iterates or enumerates through the nodes. It tells you the node number, the CPUs that are on that node, the amount of memory on the node, and it does it for each node in the system. So and then finally down in the bottom right corner in the red matrix this is a fully connected system. So if we go back to that other slide that had the X in the middle, you can see that the consequences of the cost of going from node 0 to node 1, 2, or 3 is the same. On a lower end system that didn't have the full interconnection, there would be a higher cost of going from, say, node 0 to node 3, because it would have to make multiple hops in order to get there. And that is the information that the system uses to determine if it should set that zone reclaim mode and cause paging and swapping to happen before falling over into another node for allocation. So you want to talk about this?
Yeah, sure. So indeed, we put Larry to the test often, and in fact other kernel developers. So there is actually a full talk on Autonuma-Balance. That's being done by Rick Van Riel, Vinod, and Karen later today. It's not simultaneous to this. But this is basically what can happen, okay? If you ran multi-instances, okay? Most people running servers today, they don't just run a single app. Some still do, and we have some examples of that too. But the idea is the stack chart on the left is pretty much a diagram of what you're going to get out of the box in a RHEL 7 environment without the NUMA balancing code enabled. So the sum of 4 instances of Java are giving us a throughput in billion operations per second. The Autonuma-Balance, we can check ourselves by hand tuning with what's called NUMA control. And NUMA control allows you to specify both what CPUs you run on and where the memory is. So if you understand NUMA, you know that the memory controllers are on chip, and based on the NUMA control hardware map, you can see not all memory is created equal. And that's what gives you about a 15% gain. And in fact, we've used this test with the upstream development. We've used multiple tests to basically see if the scheduler can beat the hand tuning, or at least match the hand tuning. And maybe I won't be here next year because it's already done and there's nothing to tune anymore. So I hope that's not true, or else we'll figure out more challenges in the future. Likewise, if you do want to take a single system, in this case a 24 CPU Westmere, and run the entire thing with a database, you can see we actually purposely, so it's a single app with multi-threads trying to scale up. As the threads are being scheduled, the NUMA scheduler is trying to place things optimally in the nodes to the, so basically you want the process operating on the memory that's local to the storage controller. And so you can see again, we hit probably 15, 16% improvements. And the reason we got that gain is because that's the hardware difference between getting local memory and getting memory that can be a certain percentage remote memory. And then finally, we overclock it, okay? So we basically have more threads than cores on purpose, 30 threads on a 24-core machine. Extra threads that can't, you've already kind of saturated the CPU, but a lot of applications can't always predict perfectly match the CPU with the process counts and thread counts. And so we found that the NUMA balance code continued to behave gracefully under stress. And then this is kind of visually what's kind of going on, is that these processes could splatter the memory, and in fact, there are some applications that we do want to, in fact, interleave the memory, as Larry said. But with NUMA scheduling, if it can fit them into NUMA nodes, it's going to. And of course, you have the hybrid mode where a process may be accessing maybe two NUMA nodes, or three out of 4 NUMA nodes. So doing it at the scheduler level in RHEL 7 is now possible and most efficient. In RHEL 6, there's a daemon called NUMA-D. And NUMA-D is actually a user mode tool that's going to scan the activity dynamically. So in RHEL 6, you can get auto NUMA optimization, but there is additional overhead because it's literally going to move the pages to and the processes to the cores, just like you do with the manual tools. So it's an interesting technology. Now why does this, so we spent a lot of time on NUMA. Why does this matter, right? Well, as Larry said, the chip technologies are continuing to put more cores, more physical memory per chip, multiple NUMA nodes per chip now. It used to be each chip was a NUMA node. That's starting to disappear. Hyperthreads in addition to the cores. And when you get into cloud, this stuff, you don't have the time to do the manual tuning. I certainly don't have the time, although my team has gotten larger. We still want things to be automatic and out of the box. You want the most from your hardware. And so KVM as a virtualization technology, it's just a process running on a host, a Linux host operating system. KVM is actually a process you can monitor the same way you monitor your database app or your Java app. You can move the processes to cores. You can optimize NUMA that way. And in fact, that's partly why things like OpenStack that uses KVM is a perfect match for essentially, when this optimization works on a host, it's going to manage multi-virtual guests just like it does other processes. And so, again, this is a manual way on how to control NUMA with NUMA control. In KVM, you can optimize that by either editing the XML or in Virt Manager, you can have a pull down. Our Rev product also uses the combination of TuneDs with virtual host and virtual guest, so sysctl parameters set for virtualization. And there are options to essentially optimize NUMA. And so let's see how it did with multiple KVM guests. In this case, up to 8 instances are running on an 8 NUMA node system. And in fact, the results are quite staggering once you get past, say, 2 instances. You can, what used to be a 15–20% gain on a 8-socket system is all of a sudden almost a factor of 2. So the red is what bare metal did. The yellow is actually what KVM guest did. And you can see KVM has a small fixed overhead. And you know, we're seeing our hardware partners are continuing to optimize new instructions for virtualization, but we're almost to the point of diminishing returns because it's now single digits, 3–5%, used to be 20–30% overheads with virtualization. And so, in summary, oh, okay, one more picture, and maybe Larry wants to step us through the numastat data.
Yeah, they can. I'm going to talk about this a little bit later, anyways. But there's a utility numastat, and you can watch the memory, where the memory is allocated on each node, and if there's no if you're not on RHEL 7 or you're not running numad on RHEL 6, when it goes to allocate the memory, it'll allocate it wherever it was running. If the process was running on node 1, it'll do a local memory allocation. If the scheduler decides to move it to node 2, it'll allocate memory there. So after a while, what'll happen is it'll just smatter the memory all over the place. However, using either the Autonuma-Balancing code in RHEL 7 or the numad service in RHEL 6, the system will move the process, it'll move the process and the memory all onto one node. And the performance, there will be a significant performance gain because it's not making the cross-node memory references, which can have double-digit performance consequences of doing that.
Right. And so, again, you guys can monitor your own systems. That's available in 6.5, and it was tech preview in 6.4. This numastat enhancement, so you can monitor your processes on a node-by-node basis. Sophisticated users can dig into the proc file system and find this information, and we're just exposing it with tools. So I'm going to switch gears real quick because, again, what we're trying to do is give you a crash course, and that's a week-long course. We could easily spend a full day. We're going to do it in 2 hours, so bear with us. Keep your questions if you have them, and again, if we can't answer them here, we'll answer them at the booth. The Cgroup and containers. One of the things we didn't say underneath the covers for RHEL 6 is KVM is actually using the control groups to basically manipulate the virtual CPUs and the memory. And the Cgroup infrastructure is, in fact, can be used on both bare metal or virtualized. So you can achieve some of the NUMA optimizations with Cgroups. How many people are familiar with Cgroups, too? And so a fair amount. So control groups is kind of a predecessor to containers and Linux containers that are available full feature in Red Hat 7 and a little limited feature in RHEL 6 in that we don't do network namespaces in Red Hat 6. Are we going to do that in 6? Yeah.
In OpenStack.
Yeah. So the diagram just shows how you can basically move your, you can use this infrastructure. We have a lot of partners that have used this infrastructure for their own tooling to control their workloads, etc. KVM is using this infrastructure. And so a quick database example. Another great talk we're going to recommend is later today if you want to look at database performance optimization. That's like a 420 talk. And what you can do is dynamically change the allocation of cores in memory. Like, so say during the day you have your blue job is OLTP traffic, and you have your batch jobs in, say, the red bar. And so you basically can alter the weights for the Cgroups to allow more allocation for you know, the Cgroup 2 here, the blue bar. But then at night, why give OLTP? Everyone went to bed, or for whatever reason, if you want to change that, you're not bringing instances down, you're not reallocating cores, you basically simple commands, you know, you'll see Jeremy's going to go through a little what happens in RHEL 7 to control these has built even more sophistication. There's plenty of examples, but part of this talk is we will deep dive down, and with that I'm going to share back with Larry, who's going to tell us what's happening under the covers with Cgroups.
Okay, so like Jack said, all of this container stuff that we keep hearing about, I've heard about yesterday, today, and throughout the summit here, it's layered on top of a kernel service or set of services called Cgroups or control groups. Cgroups or control groups allow you to dynamically subset your system. So if you have this monstrous system with lots of CPUs and tons of memory and network devices and all kinds of devices, you can dynamically expand and contract subsets of these systems to adjust to your workload. So basically the way that it's done is through a virtual file system or a meta file system. In RHEL 6, I sort of illustrated the default mount points, and I'm going to get into how they're used and what happens under the covers for containers in order to dynamically adjust these. So this is just an example, I put some how-tos together here. I had just a small system, 16 gigabytes, 8 CPUs, and I wanted to create a subset that had 2 gigabytes and 4 CPUs and just sort of illustrate how to do this. And the simple commands here is I do a NUMA -minus hardware to get that little printout to tell me what the hardware actually looks like. And I unfortunately didn't have space for it on the slide, but it just shows the 8 CPUs, 2 NUMA nodes, 16 gigs of memory. CPUs 0 to 3 are on node 0. CPUs 4 to 7 are on node 1, and half the memory is on each one. So I basically mount the Cgroups. I go in and I make my own little test directory, which allows, by making this test directory, you create one of these control groups. And then you can go in there and echo or write into this file system and then create your dynamic Cgroup. So I said, MEMS is the node number. So I said I want the memory from node 0 into this group. I want the CPUs 0 to 3 into this group. And then what I said is I want to limit the amount of memory in this Cgroup to 2 gigs. And then finally I say I want to run all the processes. This is the parent process. I want to run all the processes from this shell in this Cgroup. And basically what I do is I wrote a little program called run many. It allocated 20 megabytes. I said I want to create 110 processes, run in the background. And then, as you can see in the box over to the left here, even though there's 110 processes, it only ran on that Cgroup and it only allocated memory on that Cgroup. So that's basically what a container will do, is it'll dynamically create these Cgroups running within these confined environments. In this case right here, I just wanted to show you how you would, if using that NUMA -minus hardware, how you would make sure that the Cgroup that you're creating matches the underlying NUMA topology. If it doesn't, it's going to start making cross-memory references and run a lot slower. So here's just an example of correct bindings. If I say I want the memory allocated on node 1 and the CPUs allocated on node 1, I do a quick numastat to see how many hits I have. Then I run a program on there that causes a whole bunch of memory accesses, and you can see down in the bottom box, the NUMA hits went up, but the misses didn't. And then finally on the right-hand side, incorrect bindings, I did just the opposite. I said I want to allocate memory on node 1, but I want to run this on the CPUs on node 0. This is going to be all internode memory accesses, and you can see what happened over there is the NUMA misses was the one that went up, where the hits didn't stay the same at all. It's important to sort of know how all this stuff works, because you could easily go in or have scripts that go in and set up these control groups that do the wrong thing. So you have to basically make sure that they're doing the right thing. And then finally here, this is just, in addition to memory and CPUs, there's a lot more functionality and flexibility that exists, especially in RHEL 7. This is an example of what you can do in one of these Cgroups, is you can set CPUs in terms of shares, and you can say, I want this Cgroup to get a certain number of shares. The default is 1024. So if you run so I wrote two little programs. One of them is called useless and the other one is called useful. So I run enough useless programs to consume the whole system. And then in a C group, I run a useful program with 120, with the same number of shares. And as you can see with the percent of CPU, they're all right around 90% or something like that. However, if I echo a 10 in there, which is, I said, I'm only going to allow this guy to have 1% of the CPU. All the way over to the right, you can see that the percent of CPU time goes to 1. So all the other programs continue to use, well up into the 90% range, but this one that is confined to the C group only gets to use 1%. And what unfortunately I didn't have room for on this slide, using the CPU shares, if there is enough resources, it will allow a process running in a restricted C group to use as much CPU as it wants, as long as nobody else wants it. That is in contrast to what we call the CFS, or the fair share scheduler. With a fair share scheduler, if you have a C group in which you want to truly restrict, you're charging, for instance, on a per departmental basis on the amount of CPU they pay for a certain amount. What you can do is you can use the CFS file system, and using the CFS C group, there is a period and a quota. And the period is the number of microseconds that we're going to watch how much CPU that C group gets. And then the quota is how much he actually gets. So -1 says you can just have everything. So you can see what I did is I created a C group, I ran this program in the C group in using either -1, or if I put 100,000 in there. He said you can have 100,000 out of 100,000 microseconds of time. And it goes to 100% CPU time. However, in the bottom, if I echo a 1,000 in there, which is exactly what all the container stuff does, what it'll do is it'll say you're only going to have 1,000 out of 100,000 microseconds per 100,000 microseconds, and you can see down the bottom the percent of CPU goes to 1, even though the rest of the system is idle. It won't let you have it. That is in contrast with using the shares above it. And we'll get into some of this stuff as we talk more about containers.
So another quick detour. So how many people have had systems that their applications have swamped the system and basically become unresponsive and haven't, show of hands, everyone else is pretty happy. Oh, wait a minute, there's quite a few hands, Larry. So the infrastructure of C groups does allow you to control some of these resources on an application by application basis. And that's really important, because if this guy right here is running an application and we put him in a C group and in his own memory, and the rest of you are out on that other system, and he can swap his brains out in a C group and it's not going to affect you. And no offense, sir. But we will probably end up killing you as an OOM kill. And so Larry's going to give you some of those examples.
Right, and what's another important thing to say about what Shaq just said is it's dynamic. So if all of a sudden his program in the middle of the day isn't all that important, we just restrict his C group and he just gets penalized if he tries to exceed the resources we give him. But if all of a sudden his application needs to run at the close of business on Wall Street between 3:30 and 4:30, we just dynamically crank up all of his parameters and boom, he can run as much as he wants. And then finally, the last thing I wanted to talk about is OOM kills. OOM kills are, how many people in here know what OOM kills are? So that basically what happens when the system gets backed into a corner, it has to make a decision. It either has to hang the system, it has to panic, or it has to make a decision on what process is the lowest priority process that is consuming the largest number of resources and simply kill it so that the rest of the system can continue to run. And within a C group, you have OOM control is just like you do on a per system basis. And once again, I just created a small C group that's a subset of my system. I actually created the C group. I set the memory limit in bytes to 1 gigabyte, the memory plus swap to 2 gigabytes. So what's going to happen is it's going to allow it to consume 1 gigabyte of RAM plus 1 gigabyte of swap, so a total of a 2 gigabyte allocation. And I say run everything in the C group, and then finally I run a program that says allocate 16 gigabytes. And you can see down the bottom here, this is a VMstat output. In the box, inside the box, the column to the right shows the free list dropped by 1 gigabyte because I limited it to 1 gigabyte. And then finally, the amount of swap space consumed grows by 1 gigabyte because the memory plus swap is equal to a gig. But since the application wants more than that, it's going to OOM kill the thing and not affect anybody else in the system except that one process in that restrained C group. And then just to give an example of what happens if you do a D message, anybody who's experienced these OOM kills knows this. You go in there and you'll see that it actually killed just the process in the C group, and it actually tells you that it was actually constrained by the C group that caused the problem. And then finally, this, we talked about NUMA-D, and what NUMA-D does is it creates C groups. And each C group is associated with a node and the set of CPUs on the node and all the memory on the node. And what it does is it runs in the background and it looks for processes that have memory scattered among multiple nodes. If it finds them, it basically forces them to run in a C group that is a subset of the system that is basically one node. So what I did here is I unfortunately had to leave out some of the information, but I did a NUMA CTL minus hardware. I found which memory node and which CPUs are associated with the node, the NUMA node itself. And so I created one for node 1, one for node 2, and then I ran a program on node 1 that allocated, in node 2 that allocated 2 gigabytes of memory. And then basically after I run watch to watch where the memory is allocated, and if I or NUMA-D or some other service wanted to move it from one node to the other, it just simply echoes the PID into the tasks associated with that control group, and then it'll take the memory, even if it's scattered throughout multiple nodes, force it onto that C group, and then at that point it starts doing local memory allocations versus remote, and the performance will go way up accordingly. There's a lot of details here. I just wanted to show you what happens under the covers with all these containers. This is how all the container stuff works. It's a service that the kernel itself provides.
Right, and so in fact, part 2, we're going to go into how disk I/O and pushing the pages through memory works when we just go through disk I/O and other tunings that you might be able to do for OOM kills. The two things also not completely covered here is there's network C groups and there's disk or I/O C groups where you can actually throttle I/O and disk I/O and network in terms of how many IOs per second you want to allow it to do, so you can cap the quantity even if you're sharing a resource like a fiber channel card or a 10 gig net. Okay, switching gears to Jeremy with RHEL 7 and the enhancements there.
If you attended any of the keynotes, you heard the word Docker, so that's the last time I will say it. I'll use containers from now on. We got pulled in to investigate them early on in the cycle, and it really hasn't been a lot of time. You heard Solomon from that company talk about just the last year, and so this is very fast-paced. When we originally investigated what Docker was actually, dollar in the jar, was actually doing, is that it puts together more than just C groups. It uses namespaces, which are new upstream, new in RHEL 7. We have very limited ones, and even in RHEL 5 CPU sets, and in RHEL 6. It currently relies on a bridge, IP tables, and the way we're shipping it right now is with a device mapper backend. So it uses thin provisioned LVM volumes for its storage. You can give a container, way more storage than you have, betting that they'll never actually use it, just like Google does for Gmail. So each one of those systems we already kind of understand. The namespace is the only one that really adds a new twist. We've seen almost all of these before, either whether it's with Red Hat storage or with IP tables has been enabled forever. And actually, there's also one missing from here. I apologize. That's SE Linux. Larry showed you the underpinnings of what Cgroups, what you can do on the command line. The way we're actually delivering those features to customers is through abstractions like Libvirt or container tooling. In this case, if you're using Virt Manager or Virsh on the command line, and you start applying any type of, either it's NUMA affinity CPUs or whatever, it's actually fiddling those Cgroup bits for you. The same with the container technology. You're able to apply CPU affinity or NUMA affinity memory, stuff like that, to that container. So you don't actually have to go under the covers to use any of these products. In RHEL 7, you'll see systemd obviously is included, and it has this tool called CGLS, so Cgroup list, that will display the Cgroup information for that particular control group. In this case, one created for KVM, where I applied some vCPU pinning. And here's one for Docker, where I applied memory affinity. So you can see that that tool automates all the Cgroup stuff for you, Libvirt and Docker.
All right, so the next couple sections I want to talk about some tuning and some tuning parameters. What I'm going to do is I'm going to go through some of the tuning parameters that you'll see tuned in the tuned profiles, and they'll change. First thing I want to say is there's a whole ton of tuning parameters that Linux provides, and none of them are go slow versus go fast. If we had something like that, we just turn them all to go fast and everybody would be happy. What they are that every single tuning parameter is a trade-off between throughput and latency. If you want a lot of throughput, a lot of times what you do is you make the time between events really long, and you just let whatever run is running, run in there, get everything done, and then get out of the way, and then switch to somebody else. The kernel doesn't intervene at all, and that gives you the maximum amount of work done in the minimum amount of time. However, if some event, high priority event comes in and you need to service it, in a model like that, you'll wait a long time, and that's called latency. It'll take a long time. It's equivalent to making a really long light cycle out on the roads. If you change the light cycle to 15 minutes in the morning, you'll probably get the maximum number of cars through the light, but if you're stuck on one of those side roads, you're kind of screwed. So the same thing is true in the kernel. So in the kernel, we provide several different parameters, most of which I'm going to talk about are adjusted by the tuned profiles here. And we have several in the scheduler. I'll go over some of those in a minute. The finer grained scheduler tuning, there was a pretty big scheduler shift that took place between RHEL 5 and RHEL 6. And I figured there was a lot of 5 and 6 interest here. So if you have a RHEL 6 system, we're running on RHEL 5, there's a couple of parameters here that control how frequently the system potentially context switches, how big the quantum is associated with a process. That got smaller in RHEL 6 so that it's much more latency sensitive. However, because it's much more latency sensitive, the system can spend a lot more time in the bowels of the kernel context switching, and when it does that, context switching is a fairly heavy handed operation to do. If you're running on one process and you're switching to another process, you're switching address spaces. You're flushing caches and TLBs. These are hardware expensive operations to do. So I just wanted to, these two parameters, I won't spend a lot of time going over them, but these are adjusted in the tuned parameters, and I'm describing why they're changed and other reasons that you'd want to adjust these if the tuned parameter, if the tuned profile doesn't quite match your system and load. Another one is called load.
So Larry, yeah, in fact, if you are running Red Hat 4 and 5, there's really no parameter way to adjust the quantum that these two parameters now in 6 and upstream and in 7 they've been maintained. So you would be rebuilding kernels if you needed to change those. So now they're dynamic. So we change them in the tuned. Jeremy shared if you want to experiment with those. And I mean, just keep it reasonable though. I mean, going under, say, a microsecond for quantum, even today on today's fast hardware, is still a fairly dangerous thing. So
it's going to be very latency sensitive.
So those values were in
throughput,
nanoseconds.
Right. There is no one answer. That's why they're tunable.
Right.
It all depends on how your system you want your system to act.
Yeah, it's usually what, between 1 and 10 that we end up liking to set those to.
Right. So there's another section of the kernel called, or the schedule called load balancing. What load balancing is how frequently the kernel says, I want to move processes from one CPU to another. The reason you'd want to do that, for instance, is, say for instance you have 8 CPUs, every CPU has 4 or 5 processes running on it, it's well balanced. But then all of a sudden some subset of the CPUs go idle, where the other CPUs have run queues that are greater than 1 long. Initially you'd think, well, just simply shove everything onto those other CPUs to keep it as busy as possible. In a very latency sensitive way, that's the correct thing to do. However, moving from one CPU to another might imply moving from one NUMA node to the other. So you might have an application that was running really fast, and then all of a sudden the load balancer moves it from one CPU to another over to another NUMA node, and all of a sudden the performance falls. So there's a tunable sched migration cost that adjusts the number of microseconds that between these load balancing activities that happen in the kernel itself. So you can see that what we have here is we have a rule of thumb for is to increase this value in order to get more throughput, decrease it to get lower latency. There's another tunable that I don't think this is in any of the TuneD profiles, but something happened, some big shift happened between RHEL 5 and 6, and that is when one process forks another, the parent doesn't continue to run. The context switches to the child, and in general, more than half of the time, this is the correct thing to do. However, if you have an application that relies on the activity or the behavior of RHEL 5, you're going to get a performance drop, which is what basically this shows right here. And then the correct thing to do is to set this other tunable, and we'll talk about that in a few minutes, an example of that. The next thing I want to talk about here is Hugepages. The Intel x86 architecture supports 3 page sizes, 4 kilobytes, 2 megabytes, and 1 gigabyte. And we allow control of those through a couple different ways. There's a meta file system called HugeTLBFS that what you can do is you can grab a number of 2 megabyte pages and throw them on this little work list. And then if you run an application that either uses HugeTLBFS or System 5 shared memory, for instance, like the Oracle database uses this, you can actually reserve 2 megabyte pages. The benefit of doing this is the kernel really doesn't manage them. It's totally out of the picture. And the second benefit to this is each TLB entry now manages 2 megabytes instead of 4 kilobytes. Of 512 so you basically get 512 times the address space in the TLB than using Hugepages than using 4 kilobyte pages. And then finally, in RHEL 6 and 7, we have something called transparent Hugepages, which is used in anonymous memory. So if you just do a malloc, an sbreak, or an mmap anonymous, which all kinds of programs do, by default, it'll use 2 megabyte pages in those regions. And there's a significant performance boost in doing so. So in this case right here, what I did, this is just the use of standard Hugepages for like an Oracle database. Okay, you use an Oracle database. I just illustrated how they're used and how you can verify that they're actually working. So I basically said I want to reserve 2,000 Hugepages by echoing 2,000 into proc sysvm and our Hugepages, and that's exactly what the database scripts do. And then I verify that they're free. I run an application that uses half of them, and you can see half of them are freed, half of them are reserved, and then they're in use. 1 gigabyte Hugepages. Oh, what I wanted to say is with a 2 megabyte Hugepages, Once you're done with them, all you have to do is echo a 0 back into that tunable, and it throws them all back onto the free list and like they were never used to begin with. However, the hardware allows the support of 1 GB Hugepages, which is, rather than having 512 times as much information in a single TLB entry, this allows 512 squared in there. So there's a lot more information that can be managed with a single TLB entry. And this is, I just show you how it's used, how the database server would use them. The downside of these is you have to reboot the system in order to get this memory back. You have to put some arguments on the boot line, reboot your system, run your database. If you ever want that memory for anything other than 1 GB Hugepages, you have to reboot your system and then change the boot command line. Transparent Hugepages, once again, it's used for anonymous memory. It's 2 megabytes in size. There's a significant performance gain using them. So by default, they're enabled. So my first example, I shut it off, and you can see that it didn't use any non-Hugepages down the bottom. The program ran in 12 seconds. Then I don't have to reboot the system to do this either. This is dynamic. I go in and I enable them, and I run the same program, and you can see that it used all of the memory in anonymous Hugepages, and the runtime went from 12 seconds to 7 seconds. There are always trade-offs. So sometimes this is a really good thing to do, sometimes it's a bad thing to do. The problem with big Hugepages is if you touch 1 byte, you instantiate 2 megabytes instead of 4 kilobytes. So you can get a lot more fragmentation in the system. In the kernel, you can cause premature swapping and page reclaim happening when this happens and so forth. So there are times, which we'll see in some of the TuneD profiles, in which this stuff is disabled.
Yep. And so I'll give Larry the hook here. We are actually known to have what's called huge slide set, and we apologize for not leaving. We will actually be here for the next 10, 15 minutes. I know we're between you and lunch, so in summary, we actually have gone through the virtual memory subsystems and the optimizations that are available in Linux in the first part here. Tried to share with you some of the manual ways, so RHEL 4 and 5 users, the NUMA control, and some of the other monitors. Hugepages, we call them static now because there's transparent. They were just called Hugepages. And then finally, we tried to share some Cgroups and resource management that are only going further with Docker. So thank you very much. And again, appreciate that coming to Red Hat Summit.